Do you see my slides?
Yes, we can see your slides.
Okay, great. So I think I can hear myself. Oh no, it's good. It's good now. Okay, awesome. Should I start? We're good.
Yeah, we're good. We can start.
Okay, great. Well, thanks a lot for having me. Really appreciate it. I'm glad to be here. Sorry I cannot see you, but I just want to briefly talk about some of the work that we have done in the past, and there's also some of the recent developments. So I'm going to go through them in not a lot in details, but there's going to be time for question and answering, and I'll definitely be happy to answer the questions. So the topic of today is training large language models in Megatron-LM. I'll go through why we build, how we build Megatron-LM, what are the important factors, and what are the things that has changed over time and we're focusing right now. So we started looking at Megatron-LM because we wanted to train large language models, and this was in year 2019. So at the time that GPT-2 came. But at that point is also we had the philosophy of how to build Megatron-LM. We were researchers that wanted to train these models, and we wanted to build a platform that is actually good for researcher. We knew that things are going to change. We knew that it should have low barrier to entry. Those were the important things. But we wanted to get the three factors from it. So we wanted to get the efficiency. So basically, if you're using a GPU, what percentage of the theoretical peak flop you're running that, and basically how much you're wasting and how much you're gaining. So efficiency is very important because these models are expensive. There's also models were getting bigger and bigger. Right now, you're running on more and more GPUs, and scalability is very important. So first of all, you should be able to do weak scale, and also lately strong scale as well. And as I mentioned, we didn't want to build a real like a framework from the computer science perspective. We wanted to be able to build something that is good for researcher. And the simplicity was very important. So the first step that we started, what is the simplest way outside of the data parallelism we're going to do? So we started with tensor parallelism. Then we needed to scale more. We add pipeline parallelism, and then we did some efficiency with respect to the sequence parallelism as well. So our methodology in Megatron-LM counts on the 3D parallelism, data parallelism, tensor parallelism, and pipeline parallelism. So I'll briefly go through these. Tensor parallelism is basically you're breaking your network across the tensor dimension, versus pipeline parallelism, you basically do it along the layers, and data parallelism is basically the batching that is happening. So a very brief introduction to tensor parallelism and how things are done. Tensor parallelism, let's say you have a simple MLP layer. People don't use GLU right now. It was at the time that Megatron-LM was developed. GLU was the common nonlinearity. So let's say you have a matrix multiplication. I hope you see my cursor. We have a x times a, it goes through nonlinearity, and then it goes through a dropout. And then we have another multiplication that goes through dropout and output. So how we can effectively parallelize this? One approach is to do it in the way that basically you break the input the matrix along its columns, and then the weight matrices along its rows, and you will have a GLU of a summation. And since GLU is a nonlinear function, so you cannot have GLU of x1a1 plus x2a2 be equal to GLU of x1a1 plus GLU of x2. So you need to do a reduction. This reduction, which is basically all reduce, is basically adds a lot of cost, communication cost. But if you have two sequential gens with nonlinearity, if you do the first one along instead of quantizing A along the row dimension, you do it along the column dimension, then you have two separate GLU of XA1 and XA2 that you can basically parallelize. So no synchronization needed. So this results into, for example, when you have this MLP layer, into two gems that one of them is broken across as columns and the other one across as rows. And then you just need to have nonlinearity or you need to have reduction at the beginning and end of this region. So this reduces your communication by a factor of 2. F and G becomes conjugate, either a no op or a all reduce, depends on the forward or backward paths. So this basically puts the network, a transformer simply has self-attention plus an MLP layer into two regimes that are tensor parallel. So everything is serial. You go to your attention through tensor parallelism, and then you go through your MLP with tensor parallelism. So this basically these are like where the gems, majority of the gems are happening. These operations, they don't have a lot of flops in them. So as a result, if you're in the flops bound regime, then definitely this parallelization helps you a lot. But the issue arises from these sectors being serial, and I'll show you what the issue is. So basically, the issue becomes because we have regions that are replicated across different GPUs, then we need to store activation functions in those regions as well. And that doesn't get parallelized. So as a result, no matter what degree of parallelism, what degree of parallelism you use, is still like those are going to be serial. And they're going to take a lot of memory. As again, here I'm showing like models from 22 billion to 1 trillion. You increase the activation memory, which is the green one. Yes.
Yeah, I think there's, is there a connection issue on your side? Because we were hearing like, let me check if there's a connection issue on our side.
Okay. Let me check here too. I don't think so, but.
Yeah, I mean, connected to the university Wi-Fi, I think it's fine. But yeah, there was like in the middle, I think we missed a few points. Like just, I think the last 2 points that you mentioned.
Okay, I'll go back one slide then and explain.
No, I think on this the last 2 points.
Oh, I see. Okay. That sounds good. Okay. Wi-Fi on my side is also okay. Just let me know if this happens again.
Sure, yeah.
Okay. This. So basically here, if you took a look, as the model size increases, as also we increase the tensor parallel size, the activations like grow really rapidly. And for a A100, H100 that have about 80 gigabytes, you see that quickly you run out of memory. So no matter how much of tensor parallelism you use, activation memory stays constant, and this becomes an issue. So what was our proposed solution here? So basically the activations memory here with respect to formula, if these S is batch size, S is sequence length, batch size, B is batch size, H is hidden dimension, A is number of attention heads, and T is basically degree of tensor parallelism. So you can see as I increase the degree of tensor parallelism, this part of activation memory decreases, but I still have a constant of 10, which basically I cannot reduce due to this serial region. So what was our solution is actually, instead of using all gather and all reduce, or basically all reduce, we broken up the all reduce into an all gather and reduce scatter. So basically, at these regions, we have sequence parallelism, so we parallelize across sequences. Through an all gather, we go to a region that we parallelize across the hidden dimension, which is tensor parallelism. Then through a reduce scatter, we come back to a region that is already parallels across sequences, and then we go. So basically, we have a sequence parallel region, then a tensor parallel region, then a sequence parallel region, then a tensor parallel region. The good thing is, you know that an all reduce is basically a reduce scatter followed by an all gather. So basically, although we introduced now 4 operations, but the amount of bytes that we move is actually hasn't changed. because basically we broke out an all reduce into reduce, all gather, and reduce scatter. And you see what happens here? Before we had a 10 that was not divided by T. Now it gets lumped into because we go into the same region of parallelism. So as a result, now our activation memory, as we increase the tensor parallelism, is actually decreases, which helps us a lot. So this actually, and again, I'm gonna skip this part. So again, combining with something else, you can see that like for those models that I showed, we don't need to do the activation recomputation, like store it and recompute it, but we basically save almost a factor of 4 here. And you remember those, so actually we're getting a lot of perf as well as a result of not recomputing. So this was an optimization and also help us to scale better by reducing the memory that comes from the activations as well. But even scaling beyond that, that's not enough. And one thing is we can do is to parallelize not across the tensors and across the sequence, but also across the layers. So that's called pipeline parallelism. The issue with that is across layers is basically your sequential. And basically, and the trick to parallelize that is to break your batch into micro batches and try to pipeline those micro batches. So you basically go like your batch is broken into maybe 8 micro batches. You pipeline the first micro batch. Once your first layer is done, you move it to the second layer, to the third layer, and fourth layer, and all those. So you're introducing communication between layers or between groups of the layers. So that communication is not huge, but the issue is there are periods that is gray here that basically your GPUs are idle. That's called the bubble. So we introduced something called basically virtual pipelining, which basically instead of like, let's say you have GPU 1, 2, 3, and 4, instead of doing the first like 4 layer 1, the first 4 layer 2, you basically go layer 1, GPU 1, layer 2, GPU 2, and then, so this basically introduces a lot more boundaries. Your communication increases, but at the same time, you can see here that your pipeline bubble or this gray area decreases. An example, so this is good when you have basically really low batch size. So this basically virtually or interleaving. If you don't do interleaving, you see that your throughput at a smaller batch size really decreases because your pipeline bubbling is huge. But versus when you do the interleave, although you introduce more communication, but because your bubble decreases a lot, then you can get a lot of throughput. But when batch size is really large, these two are like kind of almost identical. Okay. So all these elements help a lot with weak scaling. It's basically parallelizing, fitting a lot more. And this is a little bit of older plot, but you can see that as you increase the number of GPUs and you increase the model size, you can almost stay linear there. And again, sometimes super linear because you get a lot better gem efficiency. But the issue is this, today's models is actually, there is more emphasis on scaling along the data dimension rather than the model size. Again, model sizes are big as well, but you need a lot more data. When you have a lot more data, then you need to be able to do a stronger scale. So basically, otherwise, like, yes, you're going to run at a good throughput, but if you're running on 100 GPUs, it might take 2 years to train your model. You want to run on 2,000, 10,000 GPUs to train your model in a month or a reasonable time. So what does this bring is actually, then you have a smaller batches, you have less compute per GPU, and as a result, the ratio of the communication to computation increases. You can see here that like as you scale, you deviate from the linear. This is very typical. I don't need to go through this. So my apologies. What are the things that we can do? So one thing is try to do definitely communication computation overlap. So look at the pipeline parallelism. We do a forward prop, backward prop, forward prop, backward prop in terms of like, if you use like this scheme of pipeline parallelism, and then you need to send activations and get the gradients from one to another and all those. So And this is basically non-overlapping or blocking, versus here, what we do is as soon as we do the forward prop, we issue the communication to the other GPU while we're doing the computation here of the back prop, basically, then this forward prop gets moved and then it gets fetched by the other side and those things happen. So basically communication and computation overlap. The other thing is how we can, that's basically for pipeline parallelism overlap. What can we do for tensor parallelism overlap? That's a little bit tricky. So how can we do, like, for example, we have a reduced scatter here that we're gonna see if we can parallelize the communication and computation. So basically, instead of sending the whole sequence, we basically chunk it up and basically do the gems in chunk as well. So basically, that way, you, instead of sending a huge message, you send a partial part of the message, then you get the next GPU engage into computing the gem while you're sending the other one. So basically, this is what happened. So basically, you rotate these sequences between your GPUs, and then you're multiplying them with part of the matrix, and then this final matrix you kind of compose it into smaller pieces, piece by piece, and this way, again, you go through 4 stages, you chunk them between, and then you do the multiplication, and at the end, this is how basically you fill your matrix. So this is another way to do the tensor parallelism. So this is the second dimension of the parallelism that we can do overlap with. And then the third way is also data parallelism overlap. So data parallelism is also a reduce, which you can break into a reduce, a scatter, and all gather as well. So here again, we're showing like, while the last micro batch goes through and the chunks are become available, as we go through the graph backwards, as the back gradients become available, you start communicating them. You don't wait for the whole back prop to finish and then start issuing the communication. So there are different methodologies to do this. Again, you can see mean per iteration time. So the best way is overlapping the reduce, scatter, and all gather. So ideal is basically if you can keep it constant, but you can see that if you don't do non-overlapping versus overlapping, the iteration time, overall iteration time per second decreases. So this is actually shows how it works. So these were like kind of some of the things that from the systems wise you can do and try to accelerate. But today's models need a lot more compute, and we need to try to accelerate them as well. So one way to do this, and NVIDIA chips are very supportive of this, is going through the low precision. So a lot of time we were training in BFlow 16, but we're trying to see if we can go to FP8 or even FP4. So we have actually pushed this one up to FP4. So the results I'm going to show here is not BFlow 16, not FP8, is actually FP4. So this is a training of a model up to 1 trillion token for losses up to 1 trillion token. And here I'm showing the results for a model that we trained for up to 10 trillion token as well. And as you can see, definitely NVFP4 or FP4 compared to FP8. FP8 is very similar to BFlow 16. The losses are slightly higher, but the difference here is also almost 1%. So it's not that well. And when you look at like the downstream accuracies, again, there are always fluctuation. You can see that almost they're on par. So this is actually a methodology for our large model today we use. We actually use 4-bit precision to do the work. This is another way of accelerating the models. Having said that, this introduces new challenges, because now you have, let's say you were using BFloat 16 and now you're using FP4. You have basically 4x more flops available to you. And since you have more X flop available, then as actually your GPUs are going to be starving and hungry. And as a result, as actually communication becomes even more of a bottleneck here. So what are we doing with respect to these low precisions to alleviate the communication? Here I'm showing moving communication into lower precision as well. Okay. So for example, let's take a look at this teraflops per GPU that we achieve. For different cases. The blue one is basically we do FP8 compute. So let's say we move from the bfloat 16 compute to FP8. So as a result, like communication to computation ratio decreases. So if we do bfloat 16 all gather plus FP32 reduces scatter, or gradients on an FP32 due to the precision, or parameters are still in bfloat 16. So this is our baseline. Now take a look at the red. If we move the all gather to FP8, so we gain some, but not as much. But then if we move the yellow one, shows that all gather, let's keep it at bfloat 16, but then reduce the scatter, move from FP32 to bfloat 16. We see a huge gap here. And even if we make all gather FP8, which basically are parameters when FP8 compute we use FP8 parameters as well, we can actually achieve a lot. So we can go from 350 to almost 500 teraflops per GPU, which is actually a huge saver here. So we're doing a lot of other studies with respect to tensor parallelism, how we can quantize that with respect to, again, I didn't cover MOEs. MOEs by themselves is a separate topic that we have all-to-all communication there with respect to the experts and expert parallelism. There is also this type of quantization really helps to reduce the computation, the overall iteration time. So I just want to pause here. I know I went through a lot of material, and I would like to hear if you have any questions or anything you want to know. I just want to leave you with a summary of the slides.
Thanks a lot, Mohammad. So yeah, we can, I think, open the floor to questions, and I'll try to maybe switch my camera towards the class. I guess I should have done this earlier. So maybe you can see people. I don't know if this is better. Yeah, so yeah, again, like thanks to Mohammad for the great lecture. It was like, yeah, really beneficial even to me. So we can open to questions. So people. I guess go ahead.
Well, I was gonna ask, could you go back to, I think it's like somewhere in the tens of the slides, the virtual, maybe really. Yeah. I was gonna ask if you could go back to the slide which was dealing with the virtualized pipelining.
Yep.
Maybe just go a little bit more into, exactly the intuition and some of the cost saving, all that, that kind of drove you guys to first realize this, because, it seems like this is like, maybe could have even been its own like separate work in addition to
Yeah.
Aggregating, because the paper kind of do slowly aggregation, but this is also kind of a new idea and stuff.
Sorry, what was this slow aggregation of?
Could you hear the question? Sorry, Mohammad. I think there's some chopping.
Sorry, at the end you said the slow aggregation. That part I didn't understand.
Like an aggregation of like 3 different ideas.
Okay, so he's saying that like the paper deals with an aggregation of these, like the 3 ideas, pipeline, data. But I think he wants to know, like, what made you kind of focus on this aspect, and like this itself is like a big work on its own.
Oh, I see. Okay, well, thank you. Yeah. So, gosh, the motivation is that we wanted to scale out. We were basically batch size per GPU was becoming smaller and smaller, and as a result, we didn't have enough pipeline stages to cover. So in general, for the top part, without this virtual pipelining or interleave pipelining, I don't know which one we call it in the paper. So without that, the number of micro batches you have is basically your bubble size is proportional to 1 over number of micro batches. So here, micro batches are 8. So your pipeline bubble is basically 1 over 8, proportional to 1 over 8. Now, if you have 4, then your pipeline bubble is 1 over 4, which is 25%. Basically, you're 25% of your time you're spending in the bubble. So when you increase the number of GPUs, you're basically decreasing the batch size per GPU, and also as a result, you're decreasing number of micro batches. So this basically increases the pipeline bubble. Now, we were really thinking, what can we do in those cases? And then we came up with this idea of look, if we increase the number of pipeline stages while keeping the number of micro batches constant, then that is going to reduce the pipeline bubble. But at that point, so increasing the number of pipeline stages is actually means more communication, because now that the chunks of layers that were together on one GPU then increase. So we were worried about that. So and then we did a lot of back of envelope how this ratio is gonna work out, and actually on paper worked out really well. So but this implementing this was very, very challenging. Very challenging. The code is very complex, unfortunately. Whenever I want to read it, I got to spend like few hours just to understand like what has happened and what's going on. But like kind of it started from back of envelope calculations that like, yeah, this is going to work out. I hope that answers your question.
Yeah, I think it does. Yeah, really insightful.
So let's say that we have, like, we want to decide which GPUs, like, do we buy. For example, we have the option of 5 GPUs with like 96 gigabytes and like 10 GPUs for 48 gigabytes. So like the same memory in total, but
Yeah.
which one is better? Like, which one gets the better performance in this setup?
It really depends on what you're gonna run on. Okay. So the thing is this, okay? So definitely 10 GPU of 80 is better because memory is basically either infinitely cheap or infinitely expensive. Because like, for example, if you use 5 gigabytes, if I give you a chip of 10 gigabytes versus 1 terabyte, it's not going to make a material difference to you, you see? But if you need 20 terabytes, and anything between 0 to 19 is basically useless to you. So as a result, the memory, you got to look at it as a step function. As long as it meets your need, the minimum, the better. The smaller the, like, you don't need more of that. Versus flop as always gives you speed. Okay. Having said that, again, if there is a case that really like needs a lot of memory, then definitely 5 GPUs and larger memory is going to be better, because you're going to do less of parallelism. Parallelism in general is a bad thing because it comes with overhead. Like, there's no parallelism that has 0 overhead. So if you can avoid parallelism, that's actually good. By the way, it's counterintuitive. I'm working on parallelism and I'm saying parallelism is bad, but parallelism is necessary. But if you can avoid it, you should avoid it.
Thank you for the lecture. I'm a bit curious about like the quantization in communication. So like will it have like impact on like the performance of the transport itself, despite of the throughput? And I say there's a difference to do like quantization for like or gather or reduce, like why do like the different like aggregation collective communication operations have different like effects for quantization?
Yeah, definitely. So so this is definitely important. I'm not going through the details of these things here, but look, first of all, when you do quantization, the first thing we do, first, I mean, we justify that this can actually result into speed up. Okay. So now the first thing we need to do is we need to make sure that the accuracy stays in place, because otherwise, like, I mean, you cannot just increase the speed, but then train really bad models that are not accurate. So accuracy definitely at all this stage, you got to test. And that's actually a very expensive stage for us. Like, we got to test it across different models, across different sizes, across different horizons. And that's what we do and we got to do. So that aspect is definitely there. But then there are a lot of other things that you need to have in mind. And you have really good point that different quantization has different effect for different communication. For example, when we do the quantization, when I mentioned here, quantization for reduce scatter, okay, versus all gather. For reduce scatter, we still do the summation in FP32. So communication happens in bfloat 16, but the addition into like this, when you do the addition, is actually you do it in bfloat 16. As a result, there's also the algorithms that we're using for this reduce scatter versus the reduce scatter that is here is actually different. The other thing is when you do all gather or you do all to all, there you don't have any summation, okay? So if your original tensor is in different form, you can just keep it, or you can cast it down and cast it up as long as it doesn't introduce accuracy. So there are a lot of differences and techniques and details here that I'm not discussing, but you're right, definitely all those aspects needs to be studied.
I think maybe we have time for one more question. So, you have a question?
Yeah, so also kind of going off of that question about like GPU memory. Obviously, yeah, you responded to that well, but also considering the fact that like, you know, at UMB, we also don't like, we have like a kind of, you know, I don't know, mixture of different GPU types, and they might maybe have similar memory, but they definitely have different performances in terms of like achievable teraflops and stuff like that. So do you think that would at all kind of affect these results if you were kind of forced into a situation where you were working at like maybe not as nice of a lab and you had to deal with, you know, scaling up to, you know, trillions of parameters, but can only do so across different varieties of GPUs?
Yeah, definitely. That is again, it makes the problem very hard. Fortunately or unfortunately, I haven't worked on that problem because we have had always the homogeneous clusters, but that's a very challenging work. So one thing I can tell you that close to that we have worked on is not exactly like really truly mixed, but like having pods that are exactly the same, but these pods are connected through a different bandwidths with each other. And then you gotta like really do different things. Like for example, if you have two regions that they don't have like a really good interconnect, then putting, for example, your pipeline parallelism through those links is actually good because the communication amount that you can do is actually less, and as also you can it's easier to basically overlap those. So some of those tricks we have done, but in general, if you want to optimize parallelism for really complex system, I think you got to basically model it based on simple models and try to run an optimization algorithm on it. That's something that comes to my mind, or like kind of use some heuristics. Outside of that, you're going to be probably wasting a lot of time, things waiting for each other.
Okay, I guess we're at the end of the lecture. So again, I'd like to thank Mohammad for a great lecture and for like answering all of the questions. It was really insightful. So thank you so much, Mohammad.
Well, thank you for having me, and it was really nice meeting everyone. Thank you.
Thank you.